Hello folks, this is our applications of quadratic equations video. So this is word problems. That's really what application problems or applications, that's like the code word is applications. In reality, what it really is, let me make this appropriate and use the right color here. Hold on. Word problems. Okay, so we're going to look at a couple of different kinds. So word problems for what? For quadratics, for quadratic equations. Okay, so let's start with why do we have to try to use an equation to solve a word problem? Well, it starts with because it makes us more efficient. There are some types of problems in this video, there's one type of problem in this video where it makes you a lot more efficient if you make an equation because otherwise trial and error takes a long time. Consistency is another reason because we want to try to keep things the same, and if you have a method, that method can always be applied, makes it easier. When you're doing these problems and you have to write the equation yourself, I want you to name the smallest unknown and build on it. We did that earlier this year. Excuse me. And if you're having a hard time figuring out how to write the equation, write the relationship out in words and then figure out how to construct the equation afterwards. Okay, let's start with consecutive integer problems. This one says find three consecutive positive odd integers, consecutive positive odd, three adjectives there, such that the product of the first and third is 4 less than 7 times the second. So let's start by naming our three consecutive odd integers. We're going to name them x, x plus 2, and x plus 4. Remember that odd numbers are still 2 apart. So this is your first number, this is your second one, and this is your third one. Okay? The product of the first and third. Stop. The first and the third. The product of them. So this is where this equation becomes quadratic rather than linear, because we're going to be multiplying x times x. Continue reading. Is. So the product of the first and third is my equal sign. 4 less than. 4 less than what? 4 less than the product, 4 less than 7 times the second. 7 times the second integer. So 4 less than 7 times the second integer. And there's our equation. So let's multiply through and then simplify. I can subtract 4 there, so I'll have x squared plus 4x equals 7x plus 10. I can subtract both 7x and the 10, so I can get 0 on that left-hand or right-hand side. X squared minus 3x is the balance there. 4x minus 7x is minus 3x. Minus 10 equals 0. Conveniently, I can factor that, but I can also use quadratic formula if I want to, or completing the square probably not the best method here because we actually are, we've got an odd number in the center there. So minus 5 plus 2. That's the factors of negative 10 that add up to negative 3, minus 5 plus 2, which means my solutions are x minus 5 equals 0 and x plus 2 equals 0. I got to solve those, giving me a positive 5 for this first one and a negative 2 for this second one. Now, I can go ahead and say, well, one of those is wrong. Okay, one of those is clearly wrong if I read the problem again. I'm looking for positive numbers here, so it can't be that one. And remember that I'm trying to find 3 consecutive odd integers. If x is the first one, so that means this is 5. X plus 2 is the second one, so that's going to equal 7. And then x plus 4 is the third one, that's going to equal 9. So it's 5, 7, and 9. Let's confirm that. The product of the first and third is 5 times 9, which is 45, is 4 less than 7 times the second, which is 49 minus 4, and yes, indeed, they are equal. So I know I found the correct numbers. Much more straightforward than going through and using trial and error, don't you think? Okay, let's go on to another type of word problem. All right, and a draw a picture problem. This is going to be usually something that involves some geometric figure. In this case, it's a rectangular photograph. Let's read it. A frame for a picture is 2.5 inches wide. The picture enclosed in the frame is 5 inches longer than it is wide. If the area of the picture itself is 300 square inches, find the outer dimensions of the frame. All right, so I want to start with drawing myself a little picture here. So this is the frame. And then I know I've got a picture on the inside, and I want you to pretend that this distance here is the same all the way around. So this distance right here, that's 2.5 inches. The area of the whole thing is 300 square inches, so inches squared. And we know that the length of the photograph is 5 more than the width. The length is 5 more than the width. So if the length is W plus 5, then the width has to be W. So that's inside here. That's this distance for that W, and it's this distance is W plus 5. Well, I know that W times W plus 5 is equal to 300. Why do I know that? I know that because they tell me the area of the photograph. So I'm going to solve this equation. First I'm going to distribute, so W squared plus 5W. Then I'm going to subtract 300, and I'm going to do them all at the same time. If that confused you, just write the steps out individually. Okay. Now I got to solve it. So I need factors of negative 300 that add up to 5. Now it took me a few minutes to find them and a little bit of trial and error on the calculator. But it actually turns out to be 15 and 20 are the factors of 300. So I'm positive 20, negative 15. Remember that now we solve, so I would set this equal to 0, and that means we get a W of negative 20. We'll come back to that one. Or a W of positive 15. Now, as we had before in the previous problem, we cannot include this negative because we cannot have a negative width for our photograph. Just a bad photograph, no negative width for a photograph. But I'm sure it's a lovely photograph. Why would we be looking at it, framing it, otherwise? All right, so if we get a W of 15, we now know that the width of our photograph, this width part, is 15. And the length is 5 more, which is 20, which is interesting because, remember, negative 20 didn't work because it was negative. So it kind of turns out here that because of the way this happens here with the negative 300, we actually got the two numbers. It's just that it came out that we got the negative there for 20. Don't rely on that, though. Remember, throw out your negative, use your figure to find the dimensions you're trying to find. And that's awesome. However, 15 inches by 20 inches is not the dimensions of the frame. That's the dimensions of the photograph. So how do I now find the dimensions of the frame itself, the outer frame? Well, go back and review here. Recall that we had a 2.5-inch width frame all the way around. So that means we want to take each of our dimensions, 15 and 20, and we need to add 2 times that width. Because you've got that width on the top and the bottom. You've got it top and bottom, so that's 2 of those being added to the width of the photograph, and the edge, 2 of them being added to the length of the photograph. So 15 plus 5, so this one is 20, and that's 20 plus 5 is 25. So the photograph is 20 inches by 25 inches, and that's our final answer for the problem. So we drew a picture, we made a quadratic equation. Again, a whole lot better than trying to use trial and error. Okay, and then there are the problems where they give you the equation. So when we're involving anything that involves, or we're using a problem, I meant to say, anything that involves a projectile. So if I'm kicking a football, for example, pew. Why you would kick a football straight up, I don't know. But we get the path of a parabola. We get a parabolic equation. And one of the things I can do is if I take now and I think about this on a graph, I can find out when it's going to land if I find the x value right there. In fact, it's the x-intercept, which is a 0. So we need to find the zeros of this equation. Let's read the problem. An object is launched at 19.6 meters per second from a 58.8 meter tall platform. The equation for the object height in meters, s of t, at time t seconds after launch is s of t equals negative 4.9 t squared plus 19.6 t plus 58.8. So they gave us this because we are not going to be physics students here. We are not going to be able to do that without the equation. So we don't know how to do that yet. Okay, we're not in physics. The question is, when does the object strike the ground? Now we want the x value, which is time. In this case, t value, because it's s and t. The t value, when the ball hits the ground, is the x-intercept that is further to the right. Okay, or the intercept, I should say, that is further to the right. So we need the 2 zeros. Let's find them. We're going to use quadratic formula, A, B, and C. So the opposite of B plus or minus square root of b squared minus 4 times a times c, all over 2 times a. Now, I'm going to use my calculator, of course, to do some of this stuff. We're going to end up with negative 19.6 plus or minus the square root of 1536.64. So I use the calculator to do the math on the inside because that's the path of least resistance here. And then we multiply on the bottom, we get negative 9.8. Now remember to do it each way. So you're going to have negative 19.6 plus the square root of 15.36.64. All right, so on my calculator, negative 19.6 plus, and then I put my square root of 1536.64, and then I hit enter, then I hit divide, and this one comes out to be, if I use the adding, so if I use the adding one, I get negative 2 for my answer. So negative 2 as a number of seconds, negative 2 seconds? Once again, we have to eliminate that answer. We have to drop that answer. So let's do the math again, the same thing, except this time we're using the minus. So I have negative 19.6 minus the square root of 1536.64, and then I hit enter, and then divided by negative 9.8. Oh, that's much better. That one came out to 6 seconds. And that is, in fact, our answer. 6 seconds after launch is our answer. 6 seconds after launch. So I could indeed figure out when my rocket was going to strike the ground, or whatever this is, in this case, an object. Ooh, an object. Hope it's not a person. Okay, last type of question for this. Using the vertex to solve. So this time, we're going to use the vertex. Let's look at the problem. An astronaut on the moon tosses a ball into the air. The height of the ball is represented by this equation. Again, we are given the equation because we're not physics students. We don't know how to write that yet. The variable t represents the time in seconds since the ball was thrown. So again, t is time. And f of t represents the height of the ball in feet. So again, height of the ball for the f of t, or the y value, if you're thinking x and y, and then time for the x value. Okay, or in this case t, but of course x value if we think calculator. To the nearest tenth of a foot, what is the maximum height the ball achieves? Again, we have a parabolic situation here. Now I'm definitely not drawing this to scale, like that. If we want to find the maximum height, we want to find the height at the vertex. If we want to find the height at the vertex, then we need to find the value of the ordered pair that represents the vertex and look at the y value. So we're going to do that by using our formula, the opposite of b over 2 times a. So again, that formula was opposite of b over 2 times a. Okay, it was a quiz question the other day. So now, negative 13.5 divided by, negative 5.4. So 13.5 divided by 5.4, since they're both negative, it comes out positive 2.5. So now we know that it reaches, that this case, the ball that the astronaut throws, it reaches its maximum height after 2.5 seconds. How do we find out what that height is? Well, we have to plug in our 2.5. So that means that I'm going to be, again, using my calculator, because the decimals, there's no point in me doing that out on paper right now. This is not a question of do I know how to do that on paper. It's a question of can I go ahead and find the answer. So when I put this in my calculator, I am going to make sure that I'm using the correct notation all the way across. And it comes out to exactly 30 and 875 thousandths, or 30.875. Which is the height in feet. And that's that maximum height the ball reaches. So max height. So now you can see that we do indeed use all this stuff. When are we going to use this? Well, I mean, in algebra class, but also if you were an astronaut, or if you were, into throwing projectiles and finding out when they're going to land. I mean, you can actually stop and think there'd be a lot of practical applications for this kind of math. It's just that not all of you are going to pursue careers that would use them. All right, I hope you enjoyed. Hope it wasn't too long. See you in class.